Hello, this is the next video in a playlist that I'm calling Hypothesis Testing. And here this is part 2 of a little mini-series that we're conducting on two-sided, uniformly most powerful tests in the one-parameter exponential family. And to me, it's a pretty surprising result that it's actually UMP, but it's an extension of the Neyman-Pearson lemma. And so generically the null hypothesis is that theta is less than some value or theta greater than some value, or the alternative is that it's between those two values. Now, you must watch part 1 to sort of get the full explanation of this video. And in part 1 we looked at the normal distribution with the known variance, and we were testing the mean. So this is a setting that we're in. Is the mean less than or equal to some value, or is the population mean greater than or equal to some value, or the alternative, is it in between those values? And here we're going to choose our mu1 equal to 10 and our mu2 equal to 12. Now here we have to assume that the variance is known, so we're going to pick a standard deviation of 2 or a variance of 4, and that's pretty random. I just picked it. We're going to illustrate this with an alpha of 0.05 and a sample size of 25. Now this is our test function. In the part 1, I showed how to solve simultaneously for the values of C1 and C2, which is the critical region for our hypothesis testing. And this function does it. And really it's the P norm is the probability. It's a CDF for a normal distribution. And so when we take the CDF at one point minus the CDF at another point, that's a probability. And this minus A, we want that difference to be alpha. So we're looking at the area in the critical region to be alpha. And so we're trying to find this X value, which in part 1 we call delta, that helps us solve simultaneous equations. We want this to be 0, so we want that area in the rejection region to be alpha, so that's why we subtract A here. So let's run this function, and then we use the uniroot function to find the cutoff values, and then we solve for the critical region 1 and 2, and our cutoffs are 10.66 and 11.34. Now, and that's it. That's the critical region. Now you can conduct a test. If we were to calculate the power for this function, let's create a function called power. And power is really area under the curve under the alternative region. So we're trying to calculate power between C1 and C2, which are the critical regions, and then for different values of mu. So that's what this power function is going to calculate. And let's just create this curve. And this is it. So this is the power function for this test that we just created. Is mu less than or equal to 10 or greater than or equal to 12? And the alternative, is it between those two values? And this is the power function. So notice I put a dotted line here at 0.05. So at 10, it's alpha, and 12 it's alpha, and then everything in the null region is less than that. So it's an unbiased test, which we're not covering in this video. And the power goes up, and so at some point in the middle is maximum power, which at 11, which would be around 60%. Now to simulate this region, we're going to do it for 500,000 loops or replications. And what we do is we're going to create a matrix that has 500,000 rows and n columns, and n is 25 in this case, so it's going to be a 500,000 by 25 matrix of randomly generated normal observations. So we're going to simulate it at 10, so that's a boundary point in our null hypothesis. And so let's do that. So boom, X has been created. Now we want to calculate the row means, which represents the mean from each simulated trial. So TX represents all those little means. Now we want to see if it's in the rejection region. So is it between C1 and C2? And then that'll create a true false. And if we look at the table of when it happened, there's so many trues and so many false. So this is the rejection region. So if we divide that by how many loops, that's it. So that, and it should be 0.05. So our simulated value is actually very, very close. Let's look at another boundary point, so 12, and do some simulations there. So 500,000 simulations, estimated 0.05. So that's pretty close. Now when we looked at the power curve, it looked like they had maximum power at 11 of around 60%. So let's simulate that, and this should be pretty darn close. It is 61%, so that's really accurate. Let's check a point that's a little bit deeper into the null region. And so 12.5 is deeper into the null hypothesis region. So this should actually be less than alpha, so less than 0.05. And let's look at that value. And it is. Okay, well, this is all I have for this video. As always, I'm going to copy and paste the code into the comments section. So if you want to copy and paste it into R, you're welcome to use it. And hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.